Hello dear students, welcome to Pen and Paper Chemistry. Happy to be connecting again with you on the topic States of Matter Part 3, and I am very sure and confident that by now you would have practiced a good number of questions on Boyle's law, which we covered in Part 2. Quick recall, in Boyle's law we had derived the relation between volume and pressure, saying that the two are inversely proportional provided mass and temperature are kept constant. In this video we are going to talk about Charles' law. Now we are going to take another set of two physical quantities while two more physical quantities are kept constant. So, what are we going to correlate in this particular law? Volume and temperature. So, out of the four physical quantities in the form of which a gas is expressed, we are going to correlate volume and temperature, pressure and mass remaining constant, right? And by the way, all these laws, they did not happen in a minute or in a in a week or so. It took years of hard work on the part of two scientists. So it was Jacques Charles who actually initially started working on this, and it was Gay-Lussac who actually carried it forward. So let's say a big thank you to them for giving us this interesting statement for what we now know it as Charles' law, or sometimes as Charles Gay-Lussac's law as well. What does this law say? Pressure remaining constant, the volume of a fixed mass of dry gas increases by 1 upon 273 of its original volume for every 1 degree Celsius rise in temperature. Oh, that's a lot of work, right? So why not jot it down? Get your pen and notebook ready. I am sure you would have made a separate notebook to take down notes from this channel. And if you haven't, then you should, because they will become good reference points when you are offline. You can't be going on watching videos in order to revise for your exams, right? So get going. Pause the video, get your pen and paper ready and take down the notes. Please note down this definition. I know some of you would be saying, oh, but this is not what we did in the school. The definition in the school was very, very easy. Yes, we will also make it very easy, but I am going to take your help to do that. But before we do that, there are some important terms that I am going to underline over here. The first and foremost important thing to remember here is pressure remaining constant. And second most important thing is fixed mass. When defining Charles' law, please do not forget these important terms. These are important conditions which are required for a gas to obey Charles' law. Okay? Although we shall be giving an alternative definition for this. Now let's break down this law and put it down in the form of an equation. Pressure remaining constant. Okay, done. That's taken care of. The volume of a fixed mass of dry gas increases by, right? So that means plus sign, convert it into language of mathematics. 1 by 273 of means multiply its original volume. So that means if the increase in temperature is 1 degree Celsius, the increase in volume is 1 by 273 of the original volume, right? And what we are going to do is we will assume the original volume as V0. Wouldn't that be easier for us? Right. Now let's say the temperature increases by 2 degrees Celsius. So the original volume will increase by Very correct, V0 upon 273 into 2. What if the temperature increases by 3 degrees Celsius? Absolutely. So, the volume will increase by 1 by 273 into V0 into 3. What if the temperature increases by T degrees Celsius? Also notice, all this while I am talking in terms of Celsius, I am not talking about Kelvin. So, we will have 1 by 273 into V0 into T. Simple unitary method I am applying over here, right. So, what will be the new volume? Once you have increased the temperature by T degrees Celsius, the new volume would be the original volume plus the increase in volume, right. So, let us jot down now the new volume we have stated as Vt, that is the volume at T degrees Celsius. Original volume is V0. What is the increase in volume? V0 upon 273 into T, correct? Okay. So, let us take the LCM and V0 constant 273. I will have, yes, I am going very slowly, 273 plus T degrees Celsius gives me Vt, right. Now, what you notice over here is original volume that you are going to take is constant. What is varying is the new volume or the volume of the gas is varying with respect to the temperature in degrees Celsius, correct? In other words, what is happening over here is the volume of the gas is varying directly as the temperature, that is 273 plus T, because my V0 by 273 is a constant, that is a fixed value. I am going to take a fixed initial volume. So, that initial volume of the gas does not change during the entire course of the experiment, correct? So, let us try and represent this graphically, or should we go ahead numerically only? Okay, let us do numerically only. Now, 273 plus T, you see what they did was, it is easy for me to write a single expression, 273 plus T equals to capital T, rather than doing 273 plus T every time, right. This is a constant, just now we wrote. So, volume of a fixed mass of gas, I am again repeating, fixed mass and fixed pressure. The volume of a fixed mass of dry gas at constant pressure will directly vary as the capital T. What is this capital T? Capital T is called as the absolute temperature. This is the temperature value which is accepted as the new standard according to the SI system. What is the value of this capital T? This capital T is 273 plus small t, which is the temperature in degrees Celsius. So, what do I call this capital T as? Yes, correct. T is the temperature in Kelvin, that is equals to T plus 273, or more precisely T degrees Celsius plus 273, the temperature in which the various physical quantities or physical bodies are compared, right? And the symbol for Kelvin is K, right? Now, do you recall? Yes, this particular conversion chart that I had given you for degree Celsius to Fahrenheit, degree Celsius to Kelvin. Got it? This was in part 1 of the set of videos on states of matter. So, let us now define the Charles law in the simplistic form that you are comfortable with. For a fixed mass of dry gas, volume is directly proportional to, what do you notice over here? Yes, absolute temperature, and what is remaining constant? Pressure remaining constant. Now again, I would advise you to either underline or highlight these two important terms. In fact, now we have a third one. When you are defining the Charles law, there, if you are saying for a fixed mass of dry gas, volume is directly proportional to temperature, then this law will not hold valid, because we are talking about the absolute temperature, that means temperature in Kelvin. And what has to remain constant? Correct, pressure remaining constant. So, you make sure that you highlight these two important terms. Now, why am I again and again stressing upon these things? You know, we examiners and teachers are a little particular when it comes to defining laws. Laws are very strict, right? So, you miss out any of these words, usually definitions are 1 mark. And the sad part is you miss out any of the important words or terms, that's what they give you. I know it's not good. Even I don't agree, but then I am also part of the system, right? Plus, you have to appreciate that these laws have been given by years of hard work. So, what it requires of you is to put just 2 minutes of hard work. Why and how? Please write down this definition yourself 2 to 3 times. That's all, and you will be confident about at least getting the definition right for now. Don't worry, we will get the numericals also done. But for now, let us concentrate on the definition and let us not lose that valuable 1 mark. So, what we get from here is that volume is directly proportional to the temperature in the Kelvin scale. So, we have the proportionality constant T. In other words, volume divided by the temperature in Kelvin is constant. When the pressure and the mass also remains constant. So, what formula can you put over here? V1 upon T1 is equals to V2 upon T2 is equals to V3 upon T3 and so on, right. So, this gives us the simplified view of Charles' law, which you have been familiar with. But very, very, very important point, temperature has to be in Kelvin, temperature in Kelvin. Why am I stressing on this? Because in my years of experience, I have seen students again writing the temperature in degrees Celsius. Don't laugh. We have all different types of colors in life, right? And so we have different personalities. Okay, let's continue. Now, if I have to represent this Charles' law in the form of a graph, right? So, let's understand it that way as well. So, we have graphical representation. Okay, quick test. Can you draw the graph of pressure against the inverse of volume, pressure against 1 upon V? Remember, we did it in the Boyle's law. Let me see how many of you can remember what we did in that chapter, in that particular video. Draw it. While I draw the graph for you, why don't you check your knowledge? Why don't you recall what we did in the Boyle's law? Draw all the 3 graphs that we drew in that particular chapter. Go ahead, do it. So, first of all, we will take the volume of the gas. So, here we will put volume in, you can say decimeter cube or liters or centimeter cube. And here we are taking the temperature. See, I am writing small t and this is in degree Celsius, right? Now, you notice when the temperature is 0 does not mean that the volume of the gas is 0. You can very clearly see, you see over here, when temperature is 0, so supposing this part is 0, then does not mean that the entire value becomes 0. The volume of the gas still has some number associated with it. That means the volume does not become 0, right? Otherwise, all the air would disappear in cold countries if the volume of the gas becomes 0 at 0 degrees. So, if I have to draw a graph of the volume against temperature in degrees Celsius, we notice that we will get a graph which would be something like this, correct? Because we know that there is a linear relation between volume and temperature in degrees Celsius. That means this gas, what is the temperature at which the volume of this gas will become 0? For that, what do? Let us extrapolate this graph backwards. That means we try and find out where this graph cuts the x axis or the temperature axis. Now, for the gases, it is seen that temperature is minus 273.15 degrees Celsius. Now, this is only theoretical. Why? Because if you try to bring a gas down to this temperature, it will liquefy even before reaching this particular temperature. But this gives us an important scale, and that is what we call as the Kelvin scale of temperature, or more appropriately the absolute scale of temperature, wherein the 0 will be at minus 273.15, and this is called as 0 Kelvin, right? Now, you would get an understanding why T Kelvin is T degrees Celsius plus 273. If you want to be more exact, we can also write it as 273.15. We can write it like that as well. But for a beginner, we start with 273 only at this point. So, you notice and remember, see, I am drawing this graph for temperature in degrees Celsius. How will this graph change if I am drawing the same graph for temperature in Kelvin? Let us do that. Any guesses how it is going to be? Try. So, you see, when we start with 0 Kelvin, so 0 Kelvin means the volume of the gas is 0 at 0 Kelvin. You see over here, volume is directly proportional to the temperature in the absolute scale, right? So, now if you are going to draw the graph, your graph is going to start from, yes, absolutely right, it is going to start from the vertex. It will again be a linear graph, but you see the difference in the two graphs. Here your graph did not start from 0 when you are taking the temperature in degrees Celsius, because the volume of the gas is not 0 at 0 degrees Celsius. But under the absolute scale, the volume of the gas is 0 at 0 Kelvin, right? I hope you've drawn these graphs very carefully, underlining and carefully noting the temperatures, the units in which you are expressing the temperature. Now, what you have to understand is, now like the Celsius temperature can be measured with the help of instruments, right? Now, Kelvin scale is something which is more theoretical, and it is more as an easy way to deal with temperatures. It is the standard unit. You won't have a device which is measuring or which is giving you the temperature in Kelvin. It is a conversion scale, right? So, we have also this particular temperature in Kelvin has been accepted by the SI system as the standard unit of expressing temperature, and that is why it is also called as thermodynamic temperature. What is absolute zero? Now, this is a question. Absolute zero, this is absolute zero, 0 Kelvin, but what does this 0 Kelvin correspond to? Yes, it corresponds to a temperature of minus 273.15 degrees Celsius. Don't forget the negative sign over here. So, what is absolute zero? The temperature of minus 273.15 degrees Celsius. It is a hypothetical temperature at which the volume of the gas becomes 0, or if we talk in terms of thermodynamic systems, which you will do later on, the system has lowest energy. Please don't worry too much about it right now. We shall deal with it, or we've already dealt with it under thermodynamics. Next comes the absolute scale of temperature. Now we've defined thermodynamic temperature, we've defined absolute zero. So, a scale of temperature whose 0, that is the starting point, is minus 273.15 degrees Celsius is called absolute scale of temperature. Now, unlike the Celsius scale, where you have the the lowest point and the highest point, or the Fahrenheit scales, the absolute scale of temperature will have no upper point. It is a hypothetical scale which is there to make our understanding and usage easy, right? So, if you have written this down, why not try one or two questions based on this concept to make it more clear? Okay, here is a question that I have given you. A sample of hydrogen gas occupies 500 decimeter cube at 100 degrees Celsius. What will be its volume at 0 degrees Celsius? At constant pressure. Unless I give this, you cannot apply the Charles law, because Charles law is applicable only for a fixed mass of gas at constant pressure. Now pause the video, try doing this question yourself. Go ahead, try it. Don't wait for me to do the question. Try it yourself and see the smile that is there on your face at the end of it. Have you done? Okay. So, let us discuss. As I had told you in the previous video, how do we carry out a numerical? How do we deal with a numerical? First, we jot down the data, then we check the units, we put the values in the formula, and there we see the answer and we start smiling to ourselves, right. Those are the 4 steps. So, let us start with the first step. A sample of hydrogen gas occupies 500 decimeter cube. Now, decimeter cube is volume, right. Remember the units conversion that we had done at 100 degrees Celsius. So, temperature over here is 100 degrees Celsius. What will be its volume? That means I have to find out the new volume at a temperature of 0 degrees Celsius, right. Now, let us see. So, volume, this is T1, this is T2, is it? So, do we go ahead and do like this, V1 upon T1 is equals to V2 upon T2. So, 500 upon 100 is equals to x upon 0. O upon 0, what do I do with this? Then everything will become 0, right? Am I going wrong somewhere? Yes, correct. This is not the way. What is wrong? Where did I go wrong? Tell me. Think about it. Yes, absolutely. You have to take the thermodynamic temperature over here. You have to take the temperature in Kelvin, right? Okay, now I have given you a hint over here. Try doing the question once again. So, what we will do over here, temperature here will be 100 plus 273. So, that is 373 Kelvin. For convenience, I am not taking the up to 2 decimal places, I am just taking it to 3 significant figures. So, temperature T2 over here, see 0 plus 273 gives us a value of 273 Kelvin. Always in this formula we apply or we use the temperature in Kelvin. So, what did we do while doing this numerical? We jotted down the data, correct. Did we check the units? No, we didn't check the units in the first instance. What did we do now? Yes, we converted it to the correct units, that is temperature has to be taken in Kelvin. Third step, write down the formula. Did you do that? Yes. Come on, then what is left? Nothing. You just have to put in the values and get the answer. Divided by 273. And as I had mentioned earlier, if you are not familiar with basic mathematics or you are not very confident, please revise linear equations. So, what did you get the volume as? Give me the answer. So, we should get approximately around 365.95 decimeter cube. Is it so? Am I correct? Please let me know in the comment section. Okay, one more numerical. Should we do it? Okay, I have written a question for you over here. Why don't you attempt it yourself? It says, a gas occupies a certain container at 27 degrees Celsius. At what temperature will its volume be halved? And again, what do I have to say? If you want to apply Charles' law, at constant pressure, right? Go ahead, try this question. Step 1 is the data, right? So, what is the volume? We do not know, they have not given us the volume, have they? No. And what about the temperature? Now, this time do not forget the first step itself, convert it into Kelvin. So, this gives you 300 Kelvin. Yes, even if it is not 0 degrees Celsius, still remember to convert it into Kelvin. Now, it says at what temperature. So, that means I have to find out the second temperature. when its volume will be halved. Oh my God, they have not given us the second volume as well. Let us say the initial volume is V. So, what will be the new volume? V by 2, right, because the volume is being halved, it is half of V, right. So, we have taken care of the data, we have taken care of the units, and what unit of the volume are you going to put? You can put anything, because whatever unit you put over here, the same unit you express here, correct. Next is the formula, and after applying the formula, V1 upon T1 is equals to V2 upon T2, right. Now, simply just put in the values. V2 is V by 2 into T2. So, what is T2 equal to? Yes, it was an oral question, I understand, but we needed to explain it to some of you. Okay. Now, if you notice over here, in the question the temperature has been given in degrees Celsius. My answer is still in Kelvin. What's our last step? Yes, we have to express this temperature also in Kelvin, in degrees Celsius. And how are you going to do that? Think. If temperature in Kelvin is T degrees Celsius plus 273, then temperature in degrees Celsius will be, yes, absolutely, the temperature in Kelvin minus 273. Please write down your answer and don't forget the units over here. If you are feeling confident and happy about your progress, why don't you again attempt at least 10 numericals based on this particular subheading, that is Charles' law, from any of the textbooks or books that you may be referring to, and you will find that you will feel much more confident than what you started off with, and you will definitely have a big smile on your face. By the way, looking at the numericals, can you make out what are the applications of this Charles' law? You see, hydrogen gas, weather balloons, hot air balloons, does it remind you something of that? You know that when temperature increases, the volume will also increase. So, in order to control the volume, what do we control? Yes, other than the pressure, we can also manage to control the temperature in order to prevent the gas from occupying a larger volume. And we also know that hydrogen is a very light gas. So, light gas means its density will also be lighter, correct? It will be lesser than that of the air, and we have the concept of the hot air balloons, correct? What else are the applications of Charles' law? Anything else that you can think of? Please don't forget to share it with me in the comment section. Stay connected as we carry this topic further and we do the next one, that is the Avogadro's law, and also go on to frame the ideal gas equation, right? And we are going to move from simple to complex, but in a very easy and smooth way. So, stay connected, stay safe, stay healthy. See you in the next video.